Thanks for having me. Typically, this slot in the presentation schedule is reserved for Adam, who puts in a lot of effort into making his presentation, and it's a real fun show, really. And instead, you guys this year, you guys just get me, and I've put literally zero effort into making this presentation. In fact, I didn't even make the slides. These slides are actually just a copy of what Sean has already talked in the OFI wig, but since not all of you attend the OFI wig, so I thought I should bring some of this to here. This one? Okay. Thank you. So just some legalese. I've shown this slide several times. So what is Open Fabric interfaces? It's an open source API framework that was developed since I forget 5-6 years ago, and then we were working with the application team to basically design network APIs from the top down as opposed to bottom up, which are both are valid approaches and they're trying to solve different things. But the main thing we were trying to solve was it's fine if a team like DK's wants to super optimize MPI to the lowest bits, but we should also provide a way for Fabric users to basically follow one set of framework, and that can transparently work on multiple different networks, and in the meantime also provide some optimization opportunities that allow the network fabric library to capture the application semantic. So if in the future you have network hardware that can basically efficiently perform that semantic, it does not require another application rewrite. So we are looking at this impedance mismatch between what the network provides and what the application requires. So where is Libfabric/OFI today? We have a wide variety of applications up here, and we looked at several MPI libraries, several HMEM libraries, Charm++, Chapel, and we've been doing some experimentation with various new stuff like Spark, ZeroMQ, TensorFlow, RSockets, and so on. And we have many different providers, what we call in the Libfabric terminology, which adapt to the particular network. We have Verbs, OPA, and Cray, and the Amazon EFA was added recently, and we have Network Direct for the Windows, and HPE also has a provider, which I don't think that they've submitted upstream, but it's on their GitHub repo. So in this talk, I'm going to focus on some of the new things which are happening. So there are 3 broad topics. One is the endpoint acceleration, which is quote unquote the SmartNIC API, and then the second part is more about the offload on the switches, which for the collectives. And then the third part is how the accelerators are going to fit under OFI. So all 3 are current proposals in the OFI wig, so we're still working through them. So here I'm just going to present some of the API frameworks that we are looking at, and we'll appreciate feedback from the crowd. So this is the SmartNIC aspect of it. So offloader accelerators are coming, which will have either FPGAs or like GPUs, local and remote. And there are 2 different types of acceleration, which is inline and like look-aside. Inline accelerations are that you can perform at the data rate as the data is coming in, and look-aside are typically bigger functions which require the network interface to dump into some NIC memory, and then you compute on it. So we want to expose this type of APIs up to the user, and these are enabling these functions at these specific points. And this is not just a API for launching GPU kernels or anything. This is for specifically network related accelerations. as I mentioned, so we collected some requirements of what this API should provide. So we should be able to find inline versus look aside. We need to have like necessary input that the application should be able to provide about where the memory is, where the storage is, and we can basically it basically needs to also boil down to the network protocol, which may need enhancements. Persistent and on-demand functions both are required. So we introduced a new provider capability that lets the application know that the provider is capable of these network accelerations, and we have introduced a new OFI object which has a network function, and it has a generic base, so it can apply to multiple types of objects too, and it basically says that apply this function to every outgoing transaction of this type, or you can specify per operation. So here's the API in action. We have, this is the new capability I talked about, FI network function, that indicates that the provider has the capability. And you can have various network functions that you can define. Some of the the well-known ones we can define in the public header, so that which are typical to be reproduced in multiple different providers, or we can have a provider specific, like a vendor specific operation which can be exposed here. And then this network function information is also exposed. What's the type, capabilities, and so on. And the network function primitives are mentioned over here. And you can take this network function and you can bind it to a particular endpoint that you want to apply this on. So from an application point of view, you have multiple endpoints that go to different hosts, different NICs, whatever, and then you can apply the function that you want to offload to this particular endpoint. And then you can either associate the type of data transfer when you bind it, or you can just say that I'm going to specify it when I call you. So that flexibility is also provided. And this is the network function context, which basically has the input-output parameters of the functions that is being offloaded, and the deferred work queues are a standard Libfabric feature which let you basically create work queues and post it to the network interface, but not yet run them. And then when you are ready to run them, then you can increment some counters, and it will basically fire off. This is another way of accessing the triggered operations functionality for the non-blocking stuff. Okay, so that was the first part, and then we are going to the second part, where we are talking about accelerators, not at the endpoints, but inside the network, which are mainly used for collectives, like switch-based collectives, like the vendor also talked about Sharp and so on. This is separate from the endpoint accelerations from the past few slides, and this is talking about things that we can just offload onto the switch, and it could also be abstracted as a function. It doesn't necessarily need to be limited to the MPI style collectives, and the interface we were looking for allows a generic, a little bit more generic, and doesn't expose a MPI-like API, because then OFI will just turn into another MPI, and then we don't want to replicate any of the MPI collective algorithm space in it, because as Dr. Panda knows, that there's been 1630 PhDs on just collective optimization. So we don't want to get into that space, but we want to expose what the switch's capability is to the MPI library developer or HMEM developer or something like that, so that they can use it in a portable fashion. So the switch acceleration also could be similar. You could have an inline function, or you could have a look-aside function. And then the switch accelerator is basically doing all the math here. So the operation on the switch may also require some participation from the NIC, but not in all cases. Definitely for all reduce, we don't want the NIC to do that. We want to push it onto the switch, and so on. Again, as I was saying, when we create these APIs, we look from the top down. So as a top-down example, we looked at the MPI collectives to see what are the essential parts in the MPI collectives that require really interaction from the network, not the entire set of algorithms, but what are the network-related things that the MPI collectives need. So the first thing is, how do you want to define a group? So we wanted to define what we call in Libfabric an address vector, which stands for the AV. So we wanted to define a set of them, and you can define a set by giving the count and a bunch of network addresses where your group starts and ends, and if you want a stride in it, so that you can express different types of operations. And then you can create the set once you have the attributes. And then how do you make the operations on the sets? And this basically boils down to your MPI communicator operations that most MPI users and implementers are very well aware of. Like if you have two sets, you want to create a union of them, you want to create an intersection of them, you can create a difference operation, and you can add another member to a set, or you can just remove a member from the set. So these basically map to your MPI group operations. And these deal with the low-level network addresses. So once you have created your COM world with your AV set, and then you have a COM split, you can basically use these AV set operations for implementing your COM split. And then, as I was mentioning, that this is for the offload into the switch. So the way the switch offload generally works, we looked a little bit across vendors too, that you basically have to create some kind of an entity or like a multicast group or some kind of a group thing on the switch. And we want to provide the MPI library to basically join the group. And then that's the call for basically joining a collective. Every rank has to call it. Or every participant in the collective has to call it. And then once you're done with the group, it's a standard close of the file descriptor, and you're done with the group. And then you can also query the subsystem to see which collective operations and which collective data types, how many number of members is actually supported in the hardware. So the other thing we wanted to really avoid was to make an API that basically is so high level that it needs to replicate the MPI software collective. So we want to really avoid that. So the intention is that the MPI library can basically make this call before and see what is actually supported on the platform, and then the rest it can use its own software collectors and use only the functions on the switch that are there to remove any emulation. So the NIC-based was the first presentation, the first set of things where you're defining basically a network function, and you can define whatever network function you want, and then you can bind the network function to the endpoint on which you send or receive. That's how the NIC acceleration works.
So going back to the previous question, yesterday's discussion about the offloaded collectives, suppose let's say Intel MPI is running on OmniPath, which does not have any of this support.
Yeah.
It has very good asynchronous progress capabilities because of the threads.
Yeah.
So can we, let's say for instance, when you look very collective, saying that have support for everything, go ahead and use offload or something like that. Is that possible?
Yeah, that is. So a provider can basically, there's nothing in the API that stops a provider from saying that I support the entire set. And it's fine if somebody wants to develop such a provider, but I think history shows, and I think I talked about this, not the last mug, but the previous mug, that I really wanted to avoid having the API in a way that every provider has to do it, because the algorithm space is very huge. If you remember, like I'm sure Dr. Panda does, like we've had past experience as part of an MVAPage team member that you tried to use some collective API that some vendor wrote, and they were doing a software collective, but the software collective was not as good as the MVAPage version of it, right? And then you don't know, basically how to use it. So that's what this is for. But it's fine if somebody wants to just declare everything, but they're just going to shoot themselves in the foot if they do it. So these are the actual collective operations which will happen on the switch. So these are some of the simple ones which we have defined, and I think they're very good use cases for this. FI barrier, broadcast, all reduce. A broadcast, I think Dr. Panda already showed a bunch of switch offload with the InfiniBand switches, have great performance. And then we have all reduce, also Hari talked about a lot, and I think Devinder also talked about the switch, like how the switch can help with the all reduce. All to all, I think Dan talked about how the small message all to all is critical for your QMC pack. And then all gather is also sometimes important. It depends on the application, and it's like certainly something that some of the acquisition things call for. So we added that as well. And this can be expanded. And one thing that is not there in the upstream man pages, and I'm talking with Sean, is to see how do we define the order of reductions, because MPI users will know that some algorithms that use MPI want to get the a defined order in which, say, even a commutative operation like a floating point will be applied, because you could get different results, slightly different results in the order at which the reductions are done. So we want to define that too, if you want a strict order or if you want a relaxed order. Okay, so I'm 20 minutes into my presentation. So this is the last part, which I'm going to be talking about the communication from accelerators. It could be GPUs, FPGAs, or whatever. So what's the goal over here? So if you have an accelerator which has a GPU FPGA, or it could be a persistent memory which is not really in your address space, so like how do you define the communication from it? So we want to support this PCI peer-to-peer transfer, and this audience is very familiar with this, and we want to limit the scope to fabric communication only. So we don't want Libfabric to turn into another API to spawn kernels, or conflict with something like a very low-level things like GDR copy or the P2P APIs in the kernel. So another interesting thing that what we are considering is that we should also think about supporting Libfabric running on the non-host cores, right? We don't want to define it in such a way that you can only run on a host. If you have an accelerator that you want to run your Fabric library off of, because most of the Fabric library is in user space, right? So and if the device has the right capability set, you could actually support running the accelerator, like your little bit of your Fabric stack on the accelerator. So we want to have a way for doing that. And in Libfabric, there are a couple of ways of actually doing that. And also we want to support transfers for the file system backed memory regions, right? And good use case is Optane or something. If you map it as if you have a file system, but then you mmap it because you want to access it in a slightly different manner, because now you have, one view of it is as fast storage, right? And then we want to lay out some definitions because they kind of vary across different vendors. You have the heterogeneous memory where you have like your non-host memory. This is your quote-unquote PCI device memory. And you have your unified address space, which is like your address space is unified, but the memory is mapped into the VA. And as and when you access it, pages get moved and cache lines get moved. And then you have a pure software interface where something like CUDA or OpenCL, where you need to basically allocate the memory from the device that you need to interact with, or have a pointer query function. And you could have multiple software interfaces from a single application. Like, we didn't want to preclude that because you could have different accelerators for doing different things. In the abstract sense, you can look at a code block with multiple blocks. With some are good for the CPU, some are good for accelerator X, some are good for accelerator Y. So we want to enable this mode as well. Some of the requirements that software can access directly the heterogeneous memory, like your device allocation, and but some middleware such as MPI may lose the HMEM association. So what do we mean by that? Because what we mean is that when the MPI user wants to pass a device buffer to MPI, there's no hint that it can send. So even though the application knew that it was a device memory that it's trying to send, the MPI interface doesn't let you convey that information, and that information is lost. So inside the MPI library, you have to do the query again. Or you could have, MPI is just one example, but you could have a library that is issuing the communication on some user's behalf that doesn't deal with HMEM. So we have to think about that case too. So and then like the memory can be allocated from specialized functions.
So with NVIDIA going to their managed memory, and the managed memory performance has been improving with generation on Power 9 with NVLinks, it's significantly better than on the x86 platforms. So would this be required maybe like 2 generations forward? Would the driver automatically handle it?
So there are 2 questions that you're asking over here. So one is the performance of unified shared memory with implementation of a very high performing accelerator cache line interface good enough for the application? And then the second is like whether the NIC library has to do anything with it. So the first one, I think is completely vendor specific, and I don't have any information on that. But for the second one, where the NIC library is concerned, based on my work and my personal experience, I feel like the best thing to do is to enable RDMA with your unified memory, because applications want to use unified memory. They don't want to, mark up areas that as we have seen from the application community. So they don't want to pay the tax, and you guys are already working on it, right? So if one can enable RDMA with the unified memory, I think that would be the right thing to do for the NIC stuff. So for now, we have device memory, and the device memory has the highest performance, even on systems that do offer basically a good implementation of unified shared memory. Device memory is good for the application because all the memory is local and there are no snooping, nothing going on. So device memory still remains the top performing side. And so for this support, one of the examples we're looking for is basically like a hooking provider. And what is a hooking provider is very similar to what MPI defines as MPIP or something like that. So we define a high-level hook at the top level. So at the top level, you can capture any application send, receive, and you can insert this code that will basically do this peer interface thing, like, for example, pointer query and blah, blah, blah. So so that way, if you did implement this HMEM hook, then basically you're done with all the providers. So you can, if the provider has a good peer-to-peer kernel interface with the accelerator is trying to support, then it'll just basically work with just one set of work. So I think that was my last slide. And just to summarize that, we are trying to intercept fabric offloads at 2 different points where both the NIC and the switch and the APIs should be very generic and for multiple use cases, although we are drawing a lot from MPI. And the compute accelerator APIs, that we are developing should also consider callable from the accelerator cores. And your participation is always welcome. It's free, simple, nothing to join. Just send email. Thank you.